The following is the first of two presentations I recently gave at the International Conference on 3D Radiation Dosimetry in Sydney, Australia. Now, the audience was predominantly medical physicists and chemical engineers interested in 3D dosimetry, so a certain level of familiarity with the material was assumed. I apologize if this makes some of it a little unclear, but I'm basically recording this essentially as it was presented. Hello, my name is Warren Campbell, and I'm currently working with a prototype fan beam optical CT scanner. And in my talk today, I want to highlight some developments that have taken place with the scanner since the last conference in South Carolina. I'll start off with some artifact removal techniques. I'll introduce a noise-based flask registration technique, and I'll finish off with some of our latest results. Now, to begin, here is a simple schematic of the scanner, and I'll just briefly point out some of the key aspects to be aware of. First off, it uses a laser diode module to create a 60-degree fan of red light. Also, the dosimeter is actually lowered into the tank from above, so there's no rotational stage submerged in the bath. Also, the scanner has a multi-hole collimator that very effectively rejects stray light. And finally, the detector array is an approximate arc. It is approximate in that it consists of 5 separate linear photodiode arrays. Now, let's start off with some artifact removal. Here is an image of a uniform scatterer, and as you can see, our system is susceptible to two main artifacts, rings and streaks. As it turns out, these ring artifacts come from data corruption that occurs on the edges of each of the 5 photodiode arrays that make up the detector arc. And here I've indicated the positions of the corrupted pixels in centigram space. Now, while we try to address the data corruption in the first place, we had to come up with a way of avoiding the ring artifacts that the data corruption can cause. And the key to avoiding these ring artifacts lies in the fact that the corrupted pixels lay roughly symmetrically across the detector array. So we made a change to the scanner setup. By shifting the scanner's axis of rotation slightly off-center, data corruption becomes asymmetrical. Now we take advantage of the redundancy of 360-degree centigrams. A 360-degree centigram contains two redundant, mirrored and reversed 180-degree centigrams, and we only need 180 degrees worth of data for reconstruction. So, after data is rebinned, the corrupted pixels in the front half can be replaced using valid pixels from the back half, and vice versa. Pixel by pixel, we can construct an uncorrupted centigram of 180 degrees worth of data by completely ignoring the corrupted pixels. As for the streaks are caused by two seams that run down the sides of the flasks that we're using, and the seams cause refraction errors that result in streaks. So, in centigram space, we trace out the seams, cut out their pixels, and use interpolation of nearby pixels to calculate replacement values. And here are the results after implementing these techniques. In the upper right is a raw image, and the plots shown are through the center of each images. Now, as is evident, the artifacts have been removed, and streak removal is a little more qualitative. Essentially, the seams are just gone. As for the ring artifacts, errors of up to 40% are fully suppressed. Next, onto flask registration. We knew early on that accurate flask registration would be necessary for our system. This was because we noticed that comparing pre-irradiation scans and post-irradiation scans, ray by ray, projection by projection, provided the best results. So we came up with a flask registration technique. Step 1, roughly center the dosimeter on a fiducial mark. Step 2, shift a known amount to a blank portion of the dosimeter that will go unirradiated. We deem this position the true zero position. Now, we acquire a light profile through the dosimeter and save it. This will be our key for later. At this point, the pre-irradiation scan can proceed and the dosimeter can be removed when we're finished. In order to re-register the position of the dosimeter for its post-irradiation scan, we, again, roughly center on that fiducial mark, and again, we shift the known amount to the blank portion of the dosimeter. At this point, we're roughly in the vicinity of the true zero position. So here, we acquire a survey of light profiles, where each profile is acquired from a slightly shifted positioning of the dosimeter. And somewhere in this survey is the true zero position we want to seek out. So we compare the key light profile that we saved from before to the survey of light profiles. Specifically, we calculate transmission values. So perfect placement would give a profile with a value of 1. And any mismatches in position introduce noise to these profiles. So we calculate a noise value for each profile, and then to locate the true zero position in the survey, we find the position with the least noisy transmission profile. And this is one of those surveys with the least noisy pixel already centered. Typically, it would not be centered on your first go. It would be over and up or over and down. It would basically, you'd find where the least noisy pixel is, and that would inform the shift that you would need to perform to get your system registered. As you can see, slight positioning errors introduce huge amounts of noise to these transmission profiles, angular mismatches more so than vertical mismatches. And here are some results of the registration technique. In A, the flask was not moved. In B, we've deliberately mismatched data 1 millimeter vertically. In C, we've deliberately mismatched data 1 degree angularly. And in D, we've fully removed and replaced the flask using the registration technique. Again, as you can see, angular mismatches cause more severe errors than vertical mismatches. And we can quantify the noise seen in each of these images, like so. And you notice that our fully removed and replaced flask, although it could be susceptible to both angular and vertical placement errors, it actually sees less noise than both of the images whose placement errors are either vertical or angular. We can therefore conclude that the registration technique achieves at least sub-millimeter and sub-degree accuracy. Now I'll present some of our latest results obtained with the scanner and a polymer gel dosimeter after we optimize some factors in our dosimetry protocol. And on the left, we have dose distributions as calculated by treatment planning software. In the center are quote-unquote raw images, raw in that they haven't been filtered in any way. And on the right are the same images as our raw images, but binned into larger pixels. Currently, our reconstructions have pixel sizes of about 250 microns by 250 microns, which, it goes without saying, are smaller than need be if we're going to be comparing against typical treatment planning system distributions. So binning is one obvious avenue of noise reduction. And here are some profiles that give you a real sense of just how much noise reduction is achievable through binning. It should be noted here that we've only binned within the 2D slice, which is 800 microns thick. So further noise reduction would be seen with 3D binning. But today, in conclusion, I've described techniques to remove 2 artifacts from Cinegram space. I've presented a method of flask registration that achieves sub-millimeter and sub-degree accuracy, and I've shown that even after optimizing some factors in our dosimetry protocol, binning and or filtering will be necessary for our system. Finally, I would like to acknowledge the contributions that these people have made to the project, as well as support from these sources of funding. Thank you. And at this point, there would be questions. If you have any questions, feel free to send me an email at warren.g.campbell@gmail.com. Thank you.